What up, everybody? Welcome back to some structure-free and mechanics of materials. And we got this statically indeterminate bar with torsional loading, and in particular, we got this distributed torque going on between segments A and B, and then here, nothing between segment B, C, and then segment C, D, or at point C right here, we have a concentrated torque of 20 kilonewton meter. And in case anyone needed refreshing, the double arrow means point your right thumb in that direction, and your other four fingers curl in the direction of that torque. And what we want to do in this problem is find the reactions at A and D. So the way we're going to do this is as follows. Bam. This is how we do it. We're going to do that free body diagram. We're going to set up some equilibrium equations, come up with compatibility, and solve it. First things first, let's just go ahead and do that free body diagram, and just go ahead and use the drawing that's given to you. And it doesn't matter which way you draw the reactions here. I'm going to draw like the reaction at A to the left and the reaction at D to the left. Doesn't matter how you do it as long as you're consistent. And there are no shears or moments or normal forces that we have to worry about because all the loading are just torques. Next, let's write out that equilibrium equation here. I'm going to take some of the torques equal to 0, positive to the right here, so I've got minus TA minus TD plus this distributed torque times the length of 1 meter plus the concentrated torque of 20 kilonewton meters equal to 0. And I know this is just 5 kilonewton meter per meter. And when I simplify this, it's going to look something like this. This is my first equation from equilibrium. It's one equation. I'm going to number that 1 here. But you should notice it's one equation with two unknowns, so I need another relationship to solve this out, and that's going to come from compatibility. And my compatibility relationship says that the relative angle of twist between points A relative to point D is equal to 0. And that can be broken up into all the little segments of here. So I would say this is the sum of the angle of twist in segment AB plus the angle of twist between segment BC plus the angle of twist between segment CD. And by substituting in for these segments, or the segmental angles of twist, if you will, I'm going to get another equation to solve for all these reactions that I need. The compatibility part takes the most work because really we have to find the internal torques in each segment as a function of these reactions that we've set up here, these TAs and TDs, so that we have another equation. So let's go ahead and do that. We're going to calculate the internal torques for each segment. So let's take a look at segment AB. So what we'll do when we look at segment AB is make a cut here through segment between segment AB and look and draw a free body diagram either of everything on the left of the cut or everything on the right of the cut. In this case, I'll just choose everything on the left of the cut. So here's part of my free body diagram for the cut through AB, looking on the left side of it. And here you see the TA, the distributed torque here, and you have to also remember to draw the internal torque that would be appearing at this cut here, and always draw it assuming that it's going to be positive. So this will be TAB. And also what we need here is to define a length here, or a location of this cut, an arbitrary location. I'll call this X because we have a distributed torque here, and the resultant torque, it depends on the length. So if I take equilibrium, or some torques in the positive towards the right, I'm going to get an equilibrium equation that's going to look like this. And I can manipulate this to make it to solve directly for TAB. So TAB will be, and this is my internal torque in segment AB. Now let's look at the internal torque in segment BC, which will just involve a cut through segment BC here, and I either look at the left or the right side of that cut. So here's my free body diagram for segment BC, and you'll see that I have the entire distributed torque here now over the entire 1 meter, the reaction torque at A, and then the internal torque at BC in the second segment. And I'm just going to apply the equilibrium equation to solve for TBC. So here's my internal torque at segment BC defined in terms of TA minus 5 kilonewton meters here. And now what we want to do is look at segment CD, which will just be a cut here. And when I look at the free body diagram for segment CD here, I have a choice. I could go look at all the way to the left or look at the segment on the right. And you're going to be tempted to look at the segment on the right. But what happens is if you look at the segment on the right, you introduce TD to the compatibility relationship, and you end up having to maybe a little bit more complexity in terms of solving for the two equations and two unknowns. Whereas if you consistently look at the left here, all the internal torques will only have TA on it, and when you take this back into compatibility, you'll just be able to solve for TA directly. Here's my free body diagram for segment CD, and now I just want to apply the equilibrium equation to come up with my definition for the internal torque at CD. And here's my equilibrium equation, and all I gotta do is set this up is just solve for TCD, which this will be TA minus 25 kilonewton meters. And notice here again that I have kept everything in terms of TA, and so when I substitute this back into my compatibility relationship, I'm just going to be able to get the solution or the answer for TA directly. And so here I just want to circle these, my definitions for the internal torques of each segment. Now I'm ready to substitute back into my compatibility relationship. And the thing you have to remember is that the most basic or most general definition of the angle of twist was this integral from some location to another, the internal torque Tx dx over Gj of x. And if you had a constant cross section, meaning you had a constant polar moment of inertia and a constant internal torque, this thing would become the sum of TL over Gj of the segments here. So you got to keep that in mind when we substitute back into this compatibility relationship. So for segment AB, what we had was an internal torque that varied as a function of the position or wherever we cut. So here this would be the integral from 0 for segment AB. That segment was 1 meter long, so 1 meter times TAB as a function of x dx over Gj. Okay, so I'll leave it like that for now before I substitute the internal torque back in. And then for here, for segment BC, I had a constant torque, so I could just go TBC, the length of BC, over GJ, plus TCD LCD over GJ. And all this equals to 0. Now I can substitute the definitions of these internal torques into this formula. And with this substitution, it's worth noting that, because we have a uniform GJ, or uniform torsional rigidity, and it's constant all the way throughout, we could just multiply through and get rid of it. Now when I substitute for these internal torques, it should look something like this. You'll notice here that everything is in terms of TA, and I've got one equation and I can just solve for TA. And so if I evaluate this integral now from my compatibility relationship, that's in my compatibility relationship here, I will get the following. And if I go ahead and solve this integral out, I'll get that this is TA times 1 meter minus 5 halves kilonewton meter squared. And now you'll see that all the meters are, I can divide out a meter at least here, and there was a meter here that got canceled out. Boom, boom, bam. And here, if I work this out, this thing becomes relatively simple. It becomes 2.75 TA is equal to 31.25 kilonewtons meter, and that, when I solve for TA, is 11.36. So this is from my compatibility result. If I take the TA and substitute into my equilibrium equation, I'll get that TD is equal to 13.64 kilonewton meters. And the positive results just indicate that the way I drew it initially, way back in the free body diagram section, is correct. Alright, hopefully that was interesting and helpful. See ya.